Hello, everyone, and welcome to today's webinar on multi-layer interface shear testing. I'm Andy Durham, Geosynthetic Sales Leader for Owens Corning and Vice President of the Fabricated Geomembrane Institute. I'll be your host for today's event. Today's webinar is facilitated and sponsored by the Fabricated Geomembrane Institute, which is an industry-based organization that promotes the use of fabricated geomembranes for a variety of containment applications through its research, education, and technology transfer activities. Factory fabricated geomembranes reduce field welding, reduce installation time and costs, allow for modular construction, and provide consistent seam and liner quality. The Fabricated Geomembrane Institute consists of over 40 industry members, primarily in North America. Today's first webinar speaker is Robert H. Swan, Jr. Rob is a leading expert on geosynthetic interface testing and helped draft the initial ASTM test method for geosynthetic interface testing. After completing his master's degree at Drexel University with Bob Kerner, he started the Geosynthetics Lab for Geosyntec Consultants in Atlanta and eventually opened SGI Lab with Zhang Yang. After many years running SGI, Rob returned to Drexel University as professor in civil engineering and continues to work on geosynthetic interface testing. Our second speaker today is Dr. Tim Stark. Dr. Stark is a professor in the Department of Civil Engineering at the University of Illinois at Urbana-Champaign. He has been conducting interdisciplinary research on geosynthetics and in particular geomembranes for the last 25 years, including his research on the installation and long-term durability of geomembranes and other geosynthetics in geoenvironmental and seepage applications. He's the technical director of the FGI, which is the industry organization that sponsors today's event. So before we get started, I'd like to go over just a few items so you know how to participate in today's event. The webinar is being streamed from the campus of the University of Illinois at Urbana-Champaign and Drexel University, but please feel free to ask questions by typing into the questions portal of GoToWebinar. We will try to answer as many questions as time allows at the end of the presentation. After today's presentation, the PowerPoint slides will be available on the FGI website at www.fabricatedgeomembrane.com. So thanks, and now let's have Rob begin.
Thank you, Andy, for the wonderful introduction. As Andy mentioned, my name is Robert Swan. I go by Rob. I'm at Drexel University, and my cohort in crime later in the presentation will be Tim Stark. We're going to speak about multi-layer interface testing. I have a short outline here. We're going to introduce the concept. In a way, it's similar to interface testing that we do traditionally, except the big part, we're not going to fix the interfaces to the shear box. The reason we're going to do it, we're going to talk about simulating field conditions. I'm going to provide some insight on multi-layer testing, how to prepare the specimens and the shear box, and then get into a discussion about interpreting multi-layer test results, and I'll present some pros and cons. Dr. Stark will come on then and do an extensive review of some case studies that he's been working on. So what are we talking about? Well, I know it's lunchtime. It's lunchtime here in Philadelphia. Talking about sandwich testing. You might have heard the word sandwich interface testing versus single interface testing. And the primary difference is in a single interface test, we're fixing the specific geosynthetics, if it's geosynthetic to geosynthetic, one to the upper box, one to the lower box, and conducting a single test, or have a soil and geosynthetic involved. When we talk about multi-layer, I think of it as a Dagwood sandwich, a big sandwich with multiple layers of meats and lettuce and tomatoes and what have you. But really the concept is the same. We can stack the entire lining system if it's not too complicated, or break the lining system at some point and allow us to evaluate all the geosynthetics and soil involved in the lining system at one time and measure a system strength as a function of the normal stress. So the concept's a bit different. We're letting the weaker plane fail in the multi-layer test as opposed to causing the plane to fail at a specific interface. So generally, this is the same as a regular interface test. It's a performance test. And so the conditions that we want to use need to absolutely model the conditions in the field. And in particular with the multi-layer test, that's very important because we're going to be using the site soils above and below, soil in the lower box, site soil in the upper box, to act as the clamps, per se, for the other geosynthetics in the cross section. So this is really geared to a totally performance test, and we'll talk about it, but can also be a very good methodology for quality assurance and quality control testing. So we use this test. We're going to develop data related to design of line slopes and cover systems and other geotechnical structures where you have soil geosynthetic interaction. So as I mentioned, the test conditions must closely model the anticipated field conditions. So the typical conditions that we can model, again, parallel to the single interface, we can compact our site-specific soils to the specific dry unit weight and moisture content as a function of relative compaction or relative density, whatever the specification is. We should be using our site-specific geosynthetics at this point, the ones that were spec'd and possibly collected from the field during a conformance, quality control, quality assurance testing. We also want to be operating in the normal stress range that the design calls for or the specification has called for. And with that, we want to consider what kinds of wetting conditions the interface component should experience, as well as with the soil. Should they be soaked and hydrated for a period of time and then consolidated prior to being used in the test? So all of those conditions are very much site-specific, specification-specific, and design-specific conditions. And so with the multi-layer test, we can still model the normal stress system, and we can actually monitor the normal stress transfer through the various geosynthetics in soil. We can model the shear stress as it's transferred between the layers of geosynthetics in soil, therefore modeling the complete lining system of interest, allowing us to determine the weakest planes of failure for both a peak condition as well as a large displacement condition. And yes, they may be different. The interfaces that fail at peak may be different than the ones that fail in a large displacement condition. So just going back to the single interface test, proper terminology would be a restrained or coupled test, meaning that we're specifically clamping one geosynthetic to one box, the other geosynthetic to the other, or geosynthetic in soil. And by doing that clamping, we're actually, even though we might have substrates underneath that will try to minimize the interface friction between the substrate and the geosynthetic, there's still a high likelihood of some tensioning developing within the geosynthetic because of that being constrained or connected to the one box over the other. So that tensioning may or may not be representative of what's in the field. And with that extra tensioning, we can also see some additional combing or strain softening of non-woven geotextiles as they come in contact with textured geomembranes, which could, in a way, cause much lower large displacement strengths because of that confinement. So one way to get around that concern would be to look at a multi-layer test. So the configuration down here just shows you a typical single layer configuration. And from that, if we were to run a traditional interface test series where we were running 3 different normal stresses, again on the single interface, we would get a very specific, hopefully a specific peak and then a large displacement result at some displacement, probably around 3 or 4 inches. And from them, we could then plot the measured peak shear strength, plot that against the normal stress, and determine our peak interface friction angle as well as the adhesion at peak for the interface. And then plotting the large displacement values in a traditional way, we could also measure large displacement friction angle and related adhesion. So now when we're thinking about a multi-layer test, what we're going to be looking at is now trying to build a cross-section in between the upper and lower shear box that includes as many of the geosynthetics that we can. And I've had some success up to about 6 to 7 layers of geosynthetics between my upper and lower shear box. And generally, that's more than enough to account for a typical lining system or cover system. So what happens now, if you look at the diagram, you'll see that we're going to use, in this diagram, I have a multi-layer setup from top to bottom that involves a sand. In this case, it's a wetted sand. I then have a double-sided geocomposite in contact with a textured HDPE geomembrane, and that is overlaying a non-woven geotextile, which is then in contact with wetted compacted clay in the lower shear box. So I have 6 components in this system, and you'll see that we'll have a number of specific interfaces all being tested at the same time. And the idea is once we start testing, the system will begin to shear and fail. And as it's shearing, loads are being transferred between the different layers of geosynthetics, shedding the shear stress between the system. And eventually we'll see one system that becomes dominant in the failing mechanism at peak, and then maybe we'll see a transition to a different interface at large displacement, but also it would be a function of the normal stress. So there's definitely a normal stress relationship as to when one interface may be stronger at a normal pressure than it might be at a different normal pressure. And what we actually have now is we've removed the little or no tension that can develop in the layers because none of them are constrained to any of the shear boxes. And so going back to the model, we basically now can measure the internal strength of the sand. We can measure the interface between the sand and the double-sided geocomposite. We can also challenge the internal strength of the double-sided geocomposite. We can measure the interface between the geocomposite and textured geomembrane and non-woven geotextile, and then non-woven against the clay. So now we're looking at a series of interfaces all tested at the same time. So now what we see from a typical set of results is maybe a set of curves that look like this. This is now just an example, not necessarily reflecting the system I described, but you can see that as a function of normal stresses, we could have a failure occurring on the GCL drainage geocomposite, and then at other times failing internally in the GCL or on the textured geomembrane. And therefore, we would then plot the values of the peak or large displacement strength, and chances are we would definitely see more of a nonlinear relationship because one interface may be stronger at one point but becomes weaker as the increase in normal stress is. So now we have more of a hyperbolic relationship in the shear stress, normal stress, or Moore Coulomb failure envelope. So the soils are still prepared, similar to what we would do for a single interface. They would be compacted to represent the condition of the lining system. And therefore, for example, if we have a clayey soil underlying the geosynthetics, the clayey soil should not be compacted then directly on the geosynthetics. So we really want to model the field. So in the field, the clay is going to be placed first, it's going to be compacted, and then the geosynthetic will be laid on top of it. So if we're building the system, one might think, well, we might want to put the clay in the upper shear box because if it compresses, the compressibility can be absorbed by the upper shear box. If we do that, then we would want to make sure that we compact the clay liner separate from the interface and then place it on top of the geosynthetic to represent the field condition. And that way it prevents the buildup of compaction stresses and poor water pressures at the interface. and also prevents the embedment of soil within the geosynthetic, whether it be a geocomposite or textured geomembrane. So that practice should also be done in the single interface test. Then the geosynthetics will not be attached to either the shear box in most cases, unless for some reason you have such a complicated lining system that it makes sense to split it at some point, and maybe that point could be one of the geomembranes. And there I might suggest that you would fix the geomembrane to one of the boxes and let the rest of the geosynthetics be free to do the multi-layer, and then come back and change the configuration and let that geomembrane that you fixed become free in another setup. So that's really for the more complicated lining systems. So then we basically are going to trip the geosynthetics larger than the shear box because they are going to move. So typically I found the geosynthetics cut to about 15 inches in the shear direction and maybe 13 inches in width. Granted, it's bigger than the 12 by 12 shear box, but it does allow for the shear displacement to occur on whatever interface it chooses. In that way, we're really trying to maintain that constant area of 12 inches by 12 inches. And then the last part, the geosynthetic, should be conditioned as per the specification. So if that requires the wetting or some other conditioning to the geosynthetics, that should be done as you're building the sample. And then the multi-layer interface tests, we still use a larger shear box, but we also tend to section that down to a 12 by 12 because what we don't want to occur, because we don't have the full coverage of the geosynthetic, is we don't want to cause a bearing capacity failure in the lower box due to the normal stress. So typically, I suggest that we put the less compressible soil in the lower box. So if there's a sand or gravel, which may be in a drainage layer, which would be typically above, we'll just flip the interface system upside down. And I would suggest then putting the more compressible soil in the upper shear box so that if it does compress, it's still going to maintain the level in contact with the geosynthetic rather than being compressed down into the lower box, causing the geosynthetics to be pushed down into the lower box. And then, as I mentioned, if we do that, then we want to make sure we're compacting properly. So then, with configuration of shear box, place the compacted soil in the lower box, place the oversized geosynthetics above. If you want and are familiar with using what I call telltale. Telltales would be individual wires that you could attach, or you could even use strings attached to different geosynthetics, and but preferably inextensible wire. And you could then attach that to a dial gauge or an LVDT, and you could actually monitor the individual movements of each of the geosynthetics as they're shearing to help you identify where the weaker plane is. And then finally place the soil in the upper shear box, and then continue with the rest of your direct shear setup. Yeah, of course, you're going to have to open up the gap between the upper and lower shear boxes to make sure you accommodate all the thickness of the geosynthetics. And you do also want to have a little adjustment for the soil to be exposed at the bottom of the upper shear box and at the top of the lower shear box. So what I've done, just to give you an example to lead up into what Tim will talk about, I've looked at some, I collected some data out of Ed Kabazin's paper in 2007, and I basically created a set of interface conditions that if we were to conduct them as a multi-layer test, we could analyze where the weaker plane was. So I selected for my model, based on typical results from this table, my interface model, similar to the one that I presented a few slides ahead, would be to have it such that we had the internal strength of the sand, a wetted sand to geocomposite interface, wetted composite to textured geomembrane against wetted clay, and the internal strength of the clay. So what I did was I picked typical results for the single interfaces from all of those that I just described using ITCAV's engine's data to show you that if we were to put them all in a composite way, we could clearly see from a peak point of view where the weaker planes are as a function of normal stress and how they may change. So if we're looking down here, the sand double-sided geocomposite is weaker at the lower two normal stresses, but then we see a transition occur to the texture geomembrane clay for the upper two conditions. So if we were doing this as a multi-layer series, we would actually observe this transition from the one interface to the other. But I'm doing it visually by looking at the individual interface results. And then this plot is showing the large displacement results, again, based on the data from ITCAV's engine. And again, you can see now it becomes a little bit more complicated. We actually have three different interfaces that are occurring in large displacement to define the actual minimum shearing resistance at large displacement. So what I did was I summarized all the data based on set of normal stresses ranging from 200 to 10,000 and presented the various peak strengths and large displacement strengths for each of the various interfaces. And then I gave the associated friction, peak friction angle and cohesion for soil or adhesion for the geosynthetics for both peak and large displacement, so you could see where they came from. And then I went through and I highlighted with the pinkish block to indicate where the lowest shear stress was, because we're really measuring shear stress in any interface test. So we really are looking not at the combination of friction angle and adhesion, but really the measured shear strength. And so from the peak analysis, we can see clearly that the sand double-sided geocomposite had the lowest shearing resistance from 200 to 500 PSF. And then we saw the transition, just like we saw graphically, transition from to the texture geomembrane clay interface for the normal stresses ranging from 2,500 up to 10,000 PSF. And so therefore, if I was to collect these values, I could create theoretically a multi-layer interface result summarizing the weakest shear strengths measured from 200 to 10,000 PSF that's summarized in this column. And then I could generate a best fit line to define what that failure envelope would look like, and that would have an adhesion of 120 PSF and a friction angle of 19 degrees. And then looking at the large displacement data, you can see, again, how the interfaces have shifted. Now we have three: sand to double-sided to textured geomembrane, and also clay to textured geomembrane. But we'll see that actually we went from the sand to geocomposite, then to the clay geomembrane, and then to the geocomposite geomembrane. And so with that, we got a large displacement fitted envelope of an adhesion of 105 and a friction angle of 17. So looking at them graphically, this would be, in a theoretical condition, this would be what we would expect to get from a multi-layer interface test at peak strength and again at large displacement. So this is a theoretical approach. Dr. Stark will talk about the stuff that data that he's collected doing comparison of single and multi-layer interface testing. So just to close out my discussion, there's some pros and cons that I think we should talk about related to multi-layer interface tests. The pros is the ability to analyze a complete system from clay liner to protection layer. We can see how the failure plane shifts as a function of normal stress. And we can also see failure will occur at the weakest interface or go internally through either the soil or GCL. So this approach is really good for construction quality assurance and construction quality control, because in most cases we're looking for the weakest interface, and the spec will generally be written around what is assumed to be the weakest interface. And so if you can do the entire system, you can quickly assess if your lining system exceeds or does not exceed the minimum spec within the construction specification. We're always also measuring the minimum shear strength in the multi-layer test. We're not measuring the maximum strength at any interface. It is always going to be the weakest minimum shear strength. So again, if your minimum strengths exceed the minimums required in the specification, then one can assume that the entire lining system will exceed that. And what we do, we generally see in multi-layer is we typically see a little bit lower peak strength, and we typically see a larger or a higher large displacement strength. And generally that is due to the fact that we're not generating tension within the lining system. And so we're not seeing a higher peak that could be related to tension in the geosynthetics, and we're not seeing the excessive combing that we see when we have a constrained interface, say, between geocomposite and textured geomembrane. And it does allow for a quick evaluation of materials, and I believe it better simulates the field conditions. So some cons about doing this: sometimes it's difficult to see which plane is failing first, and that's where I recommend the use of telltales. If there's some uncertainty, of course, you can take the lining system apart if you wanted to at peak and look at it specifically, or you could wait till after the test is done and carefully examine which layers were moving. There is a chance, as a function of normal stress, that the peak shear strength could shift from one plane to another, and they could also shift the planes with regard to large displacement, which could be a little complicated, again, in the reporting process. But you can always go back and do a specific single interface test to confirm the specific shear strength if you need it for your design for where the weakest plane was. As I mentioned, can be difficult if you have a lot of materials in the lining system. So some strategic splitting and then going back and assessing if you cut the lining system at some point and then rebuild the balance of it just so you can check it. The other key thing to this, and there is some pushback from a lot of the laboratories, is it's labor intensive to build it and to watch it, and really you need a well-trained technician who's familiar with testing, who is able to observe the modes of failure, and then have a really good peer review process in place from the laboratory to assure that you're getting the proper results and the proper identification of the planes of failure. I believe at this stage, I'm going to now transition this over to Dr. Stark.
Thanks, Rob.
Yep.
Okay. So on my section, I'd like to talk about the results of multi-layer interface test and then show some comparisons between multi and single. The first part of the data comes mainly from a recent paper by Dr. Shenton. Dr. Shenton is a project engineer with Advanced Earth Sciences in Irvine, California. He presented part of this data at the recent Geo Congress in Philadelphia. And so what I'd like to do is build off the paper, his paper that he wrote and gave most of it in Philadelphia. So he has a nice database of multi-interface testing, 305 points, and I want to go through the 4 main categories, as you see here, and look at large displacement strengths. Now, why large displacement strengths? If we go way back to Stark and Popple's 1994, we set up 2 design scenarios for static cases. Design 1 is peak interface strength on the base or non-sloped portions of a liner system, and then residual on the sloped or side slopes, and meeting a factor of safety of 1.5. So you can see residual or large displacement strengths are operational on side slopes, so we need that value. Second, the second design scenario is we apply the residual or large displacement interface strength on both the side slope and the base, and make sure the factor of safety is greater than 1. And the idea there is if everything goes to residual or large displacement, we still have some factor of safety and we're not dealing with a slope failure. If you use direct shear, and Rob's been primarily discussing direct shear, generally the factor of safety should be 10% higher because you are really at a large displacement and not a residual strength. The inverse analysis of the case histories indicated residual is really a better indication. And then another design scenario is if you're predicting permanent deformations on the base or non-sloped area, such as in a seismic area or due to blasting or some other external effect, of course, then you need residual everywhere or large displacement everywhere and a suitable factors of safety. So that's why I want to start out and why Dr. Shenton focused on large displacement in his 2019 paper. So for those of you that aren't familiar with side slope and base, this is a cross section from one of the case histories. You would apply peak on the base for this blue dashed area. So there's not sufficient slope or shear stress to induce detrimental shear displacements and move you from peak to residual under static conditions. But on the side slope where the red dashed line is that I'm pointing to, that has enough shear strength and shear forces or shear stresses applied to it during construction that you need a residual strength for your factor of safety calculations. And then apply residual on both of those surfaces and make sure you have a factor of safety greater than 1. The envelope is stress dependent, so you should be using a stress dependent envelope in the factor of safety calculations. Okay, with that, let's shift to some of Dr. Shenton's data. This is large displacement shear strength for a bottom liner system. In this particular case, it's a double-sided textured geomembrane with an encapsulated GCL. Two conditions: the GCL is hydrated and unhydrated. So notice the blue dots are hydrated, lower, and the green are unhydrated. And you can see the friction angle for unhydrated ranges from 13 to 16, and for hydrated about 9 to 12. The red line in between is an important line for design purposes. That's the average between the hydrated and unhydrated. So if you have an encapsulated GCL, it is common to assume that half the GCL is hydrated and half of it is unhydrated. And that way you're sort of using 50% hydrated and unhydrated. So that would be this red failure envelope. Okay, so let's move on to another interface. This happens to be large displacement strengths for a double-sided textured geomembrane with an unencapsulated GCL. So the GCL is on the subgrade and has access to moisture, and so it hydrates, and you can see the hydrated friction angle ranges from about 12 to 15. Both the prior data and this data all stress dependent. I should have mentioned that. And so you use the stress dependent envelope in the stability analysis. Another interface, multi-interface large displacement data set from Dr. Shenton is a bottom liner system with double-sided texture on a compacted soil liner or subgrade. And you can see the friction angle bumps up to 18 to 20 from the prior, a little more friction with the compacted subgrade. And then the last comparison is a side slope. And so the diagram in the prior slide was the floor or bottom or non-slope portion of the liner system. This is the side slope liner system, geotextile, smooth geomembrane on one side, textured on the back of the geomembrane, and a hydrated GCL. So you can see on the side slope a preferential shear plane or weak interface being introduced with the smooth geomembrane in contact with a nonwoven geotextile. And to promote movement along that interface and protect the liner system. You can see the friction angle now drops from about 8 to 9 degrees, and that's because that is the designed critical or weak interface. Okay, so in the paper by Dr. Shenton, he presents table 1, which is kind of a summary, a quick summary of the 4 plots that I just presented. Okay, now let's shift to 2 bottom liner systems, and this is also in Dr. Shenton's paper. There's bottom liner system 1 and 2. I'm going to focus in on the large displacement strength envelopes because there was really excellent agreement between the comparison of peak strength envelopes from both single and multi-interface test results, using the combination peak strength envelope from the single interface test and then the peak strength envelope from multi-interface. They lined up in excellent agreement. So these next slides focus on large displacement. So on the left, here is an encapsulated GCL unhydrated, and on the right is an encapsulated GCL but hydrated. So let's start the one on the left. Pretty good agreement between single and multi for the large displacement, except that this high normal stress over 2000 kPa, you can see the combination single interface large displacement envelope drops a little bit underneath the multi interface, but still pretty good agreement. Now, if we go to the hydrated encapsulated GCL, notice the combination strength envelope plots just a little lower. It depends. Sometimes the multi is large displacement's a little higher, as Rob mentioned, sometimes just a little lower, but pretty good agreement with large displacement between single and multi. Again, for these 2 comparisons here, the peak strength envelopes are in excellent agreement. The other thing to notice between these 2 plots is the left is unhydrated and the right is hydrated. So look how much flatter the hydrated envelopes are than the unhydrated, and that's the softening of the bentonite in the encapsulated GCL. Also, stress-dependent envelopes, certainly for the hydrated encapsulated GCL. Okay, so here's a second bottom liner system from Dr. Shenton's paper, and on the left is unencapsulated GCL, but hydrated, and these are large displacement. And then on the right is the unencapsulated GCL, also hydrated, but on the side slope. So the left is the floor or the bottom of the liner system, and the right is the side slope. So the normal stresses on the floor or base of the liner system are higher. So you can see the envelope is in pretty good agreement, and then an internal failure of the GCL occurs in both the single and multi-interface tests, and that results in this last point on the large displacement envelope dropping significantly down to this point. Even with a little higher peel strength of the GCL, there's still an internal failure. So this is the floor. The failure is on the GCL double-sided geomembrane interface. Now, if we move over to the side slope, you can see there's excellent agreement between the single and multi-interface large displacement strengths for the side slope. And then finally, this is some new data that Dr. Shenton presented in Philadelphia, where the GCL is taken out or not included. So this is a cover soil geosynthetic drainage composite double-sided textured geomembrane and a subgrade. The failures between the I think that's GC and textured geomembrane, and you can see there's excellent agreement between the large displacement strengths from the single and multi-interface strengths tests. Okay, so that brings me to one of the common concerns about single versus multi-interface tests. And that is that there's different displacements, shear displacements mobilized in the single interface test versus the multi-interface test. And so it's been stated in various meetings that a multi-layer test requires more shear displacement to mobilize the peak strength, which may not be true in the field or may be true in the field. It's just there's a difference. So what I did was I took the results of single and multi-interface tests for this particular project. The single interface tests are shown below in these three graphs. The first one is subgrade soil to GCL, subgrades in the bottom box, sand in the top box. GCL, texture geomembrane, sand and sand in the boxes. Double-sided drainage composite and texture geomembrane, sand in the upper and lower boxes. And so with those single interface results, you get these three sets of single interface results, from low confining pressure that I'm pointing to high confining pressure. So I'm going to go into each one of these curves and take the peak displacement, or the displacement to mobilize the peak shear stress. So this one, this one, this one, this one, and this one. And then I'm also going to take the displacement at which a fairly constant large displacement strength is mobilized. So that might be, say, 1.6 for this curve, maybe a little further, 2.4 for this curve, and so on. If it's still decreasing rapidly, like this red curve, I use the last point for the large displacement shear displacement. So I'm going to compare both the peak displacement and the large displacement strength for single and multi-interface tests. Here is the multi-interface set for the same 5 normal stresses, and this multi-interface test has the whole sandwich: subgrade soil, GCL, texture geomembrane, and leachate collection removal drainage media. So here's the comparison of the peak shear stress envelopes. The red is the multi-interface, the blue is the weakest single interface, and so you can see there's no crossover in this particular combination. The GCL double-sided texture is the critical interface from the single interface test, a little higher than the multi-interface test. The large displacement strength for this group is, okay, that's the critical interface, is shown here. So notice in the single interface test, the GCL subgrade material actually yields the lowest large displacement strength, but we don't need to use that in design because we don't fail that interface in the beginning. The weakest peak strength interface is the dark blue dots, the GCL double-sided texture, so we have to use the large displacement envelope that corresponds to that peak. So you can see that large displacement actually plots a little above the multi-interface. So now let's look at the displacements. Yep. So here is a plot of the peak displacement from the multi-interface tests on the vertical axis and the peak displacement from the single interface tests on the horizontal axis. The line that you see in the diagram is a 1-to-1 line. So if any of the points plot on this 1-to-1 line, that means that the multi-interface and the single interface test yielded the same displacement to mobilize the peak strength. In general, from this data, it actually looks like the multi-interface has more points at a lower shear displacement than the single interface, but still within reason of the 1-to-1 line. So in this suite of tests, there isn't a big difference between the peak displacement required for the single and multi-interface tests. Okay, so let's shift gears to the large displacement. which is on the next slide. So using the large displacement from multi-interface on the vertical axis and the large displacement single on the horizontal, 1-to-1 again would be equal. You can see a little more scatter because, again, none of the curves really reached, well, some of the curves reached a constant minimum, but a lot did not because it's a direct shear test. You can see there's more scatter on the large displacement strength, but they're all scattering about the 1-to-1 line. There's a point over here where you can see the large displacement from single interface is less than an inch and about 1.6 or 7 inches from the multi-interface. But again, scattering about the 1-to-1 line. So if this data set, not a huge difference between single and multi-interface shear displacements. Here's one more quick comparison. This is peak strength from a bottom liner system. Good agreement. The dashed line is single interface right there, and the solid line is multi-interface peak. And here are the large displacements, and excellent agreement there. Okay. So in summary, from Dr. Shenton's paper, and then I'll wrap up with the next slide with some general comments. The main summaries from his paper are it's a good database for multi-interface tests, so you can use that database certainly on the large displacement side to check your single and multi-interface large displacement strengths and make sure you're in the right ballpark. Excellent agreement between single and multi-interface tests for peak strength envelopes in this database. Large displacements are good to excellent, as I showed some results. Multi-interface results look reliable and repeatable. They do eliminate issues with clamping the geosynthetics, as Rob mentioned. They represent the field conditions, and you need one liner system configuration tested instead of 3 or 4 single interfaces. And I think it's time to develop a standard for the multi-interface test through ASTM. That has been proposed recently. It's now part of 5321, but I think as it takes shape, hopefully it'll become its own test method. So recommendations: use a different strength envelope for the side slope and base of liner systems. There are different configurations, normal stresses and strengths, and geosynthetics involved, so there should be a different strength envelope for the base and side slope. Don't necessarily use the same strength envelope for both. If single interface tests are specified, you could use a multi-layer test to verify the peak and large displacement combination envelopes. If there's an anomaly with a multi-layer test, which is specified, you could conduct a relevant single interface test to resolve that anomaly or shed light on it pretty quickly. If single interface tests are specified, require a strength envelope, not a specified strength. Put the entire envelope in the specifications and then have the suppliers meet that strength envelope because the envelopes are stress dependent. Okay. And that's the last recommendation as well. Okay, so here's some contact information for Rob Swan, myself, Andy Durham, and Jen Miller of the Fabricated Geomembrane Institute. Please check the FGI website for some new features. And next webinar coming up is on geofoam with Professor Bartlett of the University of Utah in May. And Andy, I'd be happy to try to answer questions if there are questions.
Yes, thank you, Tim. We're going to start with a few questions that were directed to Rob Swan. Rob, are you still on the line with us?
Yes, I had to remute.
Okay.
I have about 2 minutes.
Okay, great. So we'll try to do this quickly. On your slide number 8, Rob, the question from Rahul Solanki is, if you keep the clay in the lower box, won't it result in losing the shear plane?
Yeah, that's why I recommend not doing that.
Okay, great.
In my diagram, yeah, I show it in my diagram like that, but if I was actually going to test it, I would flip the entire system upside down and put the clay in the upper box and the sand in the lower box.
I got you. Okay. The next question from Garish Kumar is, on slide 23, is there a maximum number of materials that can be tested in a multi-layer shear testing? And I think you answered to me in a chat that it would be up to 5 or 6, but if you want to clarify that.
5 or 6,
Okay.
really governed by the thickness of the geosynthetic. So if you have a really thick triplanar geocomposite or a couple of them, then you might be limited again by the gap that some boxes can handle. Yeah.
All right. And then from James Hoover, for a double-sided GCL, what is the sample size that you would test in an in-house tensiometer?
In-house tensiometer?
Yeah, and I guess if you're trying to do some, I guess laboratory conformance testing as a.
I would suggest that you do an 8-inch wide, a wide width specimen.
Okay.
Using like a Curtis grip or some kind of grip where you can grab both the geotextile and the geonet.
Okay.
I believe there's an ASTM standard for that test. I don't know.
Okay. Great. And then the last question for you, Rob, is from Riva Norje, and they ask, has a failure between the components of the DSGC occurred in multiple interface tests?
Yes, it can.
Does that make sense? Okay. Okay.
Yeah. You can have an internal failure within the geocomposite, just like you could just in a single interface. However, it may be more pronounced because of the gripping on the single interface. You're gripping all the components, but you may still break that bond between the geotextile and geonet. In the multi-layer, they're all free, so if that bond is has a low peel strength, there's a good likelihood that that will break, and that will be your weak plane.
Okay. Great. Well, thank you, Rob. If you need to go, we appreciate it. Tim, if you'll stay on the line for a few more minutes, we still have a couple more questions for you.
Yep.
Okay. But thank you for your participation today, Rob.
All right, thank you.
Tim, are you on the line now?
Yep.
Okay, so another question from Rahul Solanki. Is partial increase in residual strength compared to peak strength for single interface tests possible for any geosynthetic combination?
So you
Does
said,
that make sense?
well, wait, you said partial increase?
Yes, is a partial increase in residual strength as compared to peak strength for a single interface test possible for any combination? Is that possible?
I think what's being asked is, after you reach residual or large displacement, can you get a strength gain?
Yeah, I think that's what he's asking. Maybe what we'll have to do is have you clarify that to Rahul offline with an email.
Okay, but if it's just geosynthetic, probably not. If it's, say, hydrated bentonite or a high moisture content subgrade / compacted soil liner, maybe there's some consolidation and you can gain some strength that way. But in general, the geosynthetics are damaged at large displacement and they don't heal.
Sure.
Yep.
Okay, that makes sense. I'm going to move on to a couple more questions here, as long as we have some more time. One of the it was asked if you could provide full citation for the Shenton reference, and I think that shouldn't be a problem. So we can send that out via email after the presentation.
And here it is on the screen, Andy. I've got it highlighted on the screen. And if people want a copy of the paper, I'd be happy to email it to them.
Okay, so this one's a little bit in depth. So if you want to follow along with me, Tim, this question comes from Nick Rocco, and he says he struggles to validate combination of different shear interfaces from one multi-layer shear box in terms of actual failure modes in the field. In his experience, the failures are typically along one interface, not a combination of interfaces. Are you aware that any documented failures along a portion of the slide plane above the geomembrane and a portion below the geomembrane? I think he wants to know if the construction of a composite failure envelope makes sense in terms of the lab data, but does it also make sense in the field failure modes? Does that make sense to you, the question?
Yes.
Okay.
The answer is great. First, great question. There is
Okay.
absolutely field evidence that the critical interface changes with normal stress. And that's one of the key findings of this paper, Stark and Popple 94, from the Kettleman Hills slope failure, that on the base or the flat portion, and in fact, this is the cross section of Kettleman Hills right here, on the blue area, sliding occurred at the interface between the secondary geomembrane and the compacted soil liner underneath of the geomembrane. But when the normal stress decreased along the side slope, sliding actually occurred on the geomembrane interface. And there's some great pictures showing the different, I gave a webinar, I think it was the first one in this series, and showed the photographs from that. So if you'd like to look at those photographs, I can show you. But that case history is important for many reasons, but a couple of them are stress-dependent envelopes. The critical interface changes generally from the side slope to the base, and that's why one of the recommendations is don't use the same strength envelope for the base and the side slope, because the normal stresses are different and you'll have a different critical interface. So good question, and there are field cases that show that.
Great. So moving on, this question comes from Shaheen Ghazi Zaida, and he asks, what was the peel strength of the GCL in Dr. Shenton's paper? Does that partial interface and internal failure mode, was it observed in the multi-interface test as well? Do you remember that?
Good question. I've got part of the paper here in front of me. Let me see.
If that's something that we can address with Mr. Zeta offline, I'm sure he'd appreciate that.
Okay. All
right. He also asked, though, the lower envelope for the hydrated GCL compared to the dry GCL.
Okay.
Could this be because of bentonite extrusion? How often does that occur in the field, and what are the displacement rates and interface shear tests? I guess he's asking, about bentonite content and stability within, hydrated versus dry GCLs.
Okay. So first, I found the increase in peel strength that's shown in the diagram that's on the screen. It increased from 2,100 newtons per meter to 2,500 newtons per meter. Okay. Right. Now let's go back to the hydrated versus unhydrated. Yes, there is some extrusion of bentonite through, say, a woven or even a non-woven, depending on the thickness of the non-woven, that reduces the strength, as well as the bentonite lubricating the reinforced fibers and allowing the GCL to shear internally easier. And that's some differences between the green line, which is unhydrated, and the blue line, which is hydrated.
Understood. Okay. Great explanation. We got just a few more. On slide 26, I can't remember, slide 26 was Rob's or your slide.
I got it. It's on the screen.
Okay. Yep. So this is Marisa Vander Weisduzen, and she asks, when you have an earth embankment acting as a buttress on the toe, would you use a peak or residual on that toe Example, maybe a three horizontal and 1 vertical slope.
Okay, so the question is, and if I build a buttress here with my cursor out here on the toe and bring it down to the ground, should you use peak underneath the buttress or residual? In that particular case, I think you could use peak because the interface is not sloped. In other words, it's close to horizontal, so there shouldn't be detrimental shear stresses developing at the toe.
Okay. No, that makes a lot of sense. It looks like our last question from Mike Hollum is, how do you check pore pressures? I guess in the interface test, and I'm not sure if that's specific to laboratory or field. Would you have an answer for that?
Yeah, so let's do it in the laboratory. That's where it's been tried. Some pore pressure transducers have been introduced into GCLs to try to measure the shear-induced pore pressures. Some mixed results. There's some data on that in the state-of-the-art paper by Fox and Stark on GCLs. But in general, it's difficult to measure pore pressures. Even in the laboratory, the transducers must be saturated and so on. So the way that is controlled is through the shear displacement rate, making sure the specimen is sheared slow enough that it's in a drain condition.
Okay. Great answer. We're going to go to the last question was a follow-up from Maurice after your explanation on the buttress. I'm not sure if you'd see this, but what if the liner is placed over the buttress? What is that? Would that be a scenario?
Oh, okay. Now I see where that question was going. So yeah. The question is, I'll draw a pen. So if we build a buttress here at the toe, like this, and we actually bring the geosynthetics up and over, should you use residual or peak on this side slope? If that's the design scenario and waste is placed, say, from there up like this, and the liner system is supporting that waste, I would use large displacement / residual on that piece because that's really very similar to the side slope over here where the red dashed line is.
Okay, great. That's all the time that we have for questions today. We thank both Tim and Rob. Before we wrap up, I'd like to mention some ways to become more involved with the FGI. Please visit our website at fabricatedgeomembrane.com for access to technical material, including test method videos, installation guidelines, details, white papers, research reports, and more. And also, please contact us, either Dr. Tim Stark or the FGI Director, Jen Miller, if you'd like to participate as a guest in our monthly member teleconference. So thanks today to our speakers, and have a great rest of your day.
Great. Thanks, Andy.